Hey, hello everyone. My name is Zhuang from UC San Diego. So I would like first I would like to thank the organizers for inviting me to present this lunch talk for the Generative AI program. And I was asked by the organizer to explain in my talk why does a group of physicists wants to hold a program of artificial intelligence in KITP. As AI nowadays becomes a part of theoretical physics now. So I think these questions may have different answers to different people. Therefore, so my response to this question will also inevitably have my own bias and also my own opinion. So I hope that my words will be considered as an invitation to discussion other than a final answer. So perhaps one convincing evidence to this question is 2024's Nobel Prize in Physics awarded to John Hoffield and Geoffrey Hinton for their foundational contributions that enables machine learning with artificial neural networks. But in my opinion, what they have created actually goes beyond neural network. They open up a new field of generative modeling and statistical machine learning, which deeply roots in those same ideas that has guided physics for centuries. So today I would like to explore this shared foundation between physics and generative AI, and I want to explain how generative AI is not only a tool for physics, but also in more profound sense, an extension of physics itself. So long story short, let's first explain. So what is generative modeling? So generative modeling starts by given a data set where you have samples that is drawn from an unknown data distribution P data of X, where X stands for the sample, and then you try to learn a probability distribution of the sample parameterized by a set of parameters, such that the parameterized distribution approaches the underlying data distribution as much as possible. So this can be achieved by minimizing certain distance measure between these two probability distribution. One commonly used measure is the KL divergence between the, let's say, the data distribution and the model distribution, which goes like sampling from the data and then evaluating the log likelihood P data of X divided by P theta of X. Suppose we can evaluate the model log likelihood, then we can compute this KL divergence by sampling from the data set, and then we can use gradient descent to optimize this objective function in order to find the optimal value of the parameter. So that constitutes the whole training of the generative model. So we can see that essentially the generative modeling is a task which tries to infer the underlying data distribution from samples of the data. So the canonical way to solve this problem is actually by keep sampling and then do a histogram, right? And then this kind of canonical method, histogram methods, will incur a huge amount of data. So it's not very efficient. Generative modeling is just a more data efficient approach to find the underlying distribution. But it has assumptions. You need to assume that this data distribution has some structure that, such that it can be compressed into some tractable parameters, such that if the data is compressible, then probably you can use polynomial resources to learn the underlying distribution. However, this assumption may not always be true. If that is the case, then we say that the data distribution is unlearnable. And we actually will encounter some of these cases later on. So everything boils down to design a good model to to model the probability distribution, and we have some desired features for a good generative model. First of all, a generative model must provide efficient sampling. Meaning that we need to be able to sample new samples from the learned probability distribution efficiently and accurately. And then secondly, so that constitutes the name of generative model, right? It generates new samples. And secondly, you need to provide likelihood estimation. Meaning that we can compute the log probability distribution for any sample, not necessarily in the data set, any sample you're given to it. And then a third requirement, actually not a requirement, it's an extra requirement. It's actually a gift. It's representation learning. Because the assumption of generative modeling is that there is some way to compress the data. So show me the compression, meaning that in some cases, it's possible that the data distribution can be written as drawn the data from some latent variables. So this Z is some latent features, and then this latent feature is usually more compressed that you draw from the prior distribution of latents and use latent to generate your data. So in this way, you learn a more compressed representation of your data. So this is an unsupervised manner and a data-driven manner to learn efficient representations of data.
How would that second desired feature usually fail or estimation?
Yeah, this is not always provided by a generative model, so it needs good design. So these desired features are features for good generative model, and generative model that all generative model will provide the first functionality, but not necessarily the second and third. If they provide all the functionality, we deem it to be good. Okay, so that's so then that leads to the question how to model, because we have these desires, right? So we want to ask how to model a probability distribution. A very essential feature of probability distribution is it's a number, a real number that is greater equal than 0. And as a physicist, all I learned so far, to make a number positive, there are only two different ways. One is to raise a real number to the exponent. The other is to take a complex number and then square it. So that corresponds to two different ways in physics that you can come up with a positive real number. So the first approach is called statistical physics. And the second approach is called quantum mechanics. So they correspond to two basic generative models. The models probability distribution P of X in two different ways. So the first approach in machine learning community is called Boltzmann machine. Because it's a Boltzmann distribution. And then the second approach is called Born machine. Because that's the Born distribution. And Boltzmann machine is also called energy-based model, probability model. Okay, so let's first discuss Boltzmann machine. So Boltzmann machine or energy-based model boils down to creating an energy function that models the probability distribution. So the most general energy function you can write down for some sample can take the form like you first consider one body term of your sample And then there's two-body interactions, theta ij, two-body interaction of xi, xj, and then maybe there's three-body interactions, theta 3 of ijk, xi, xj, xk, and so on. So that's the most general energy function. And definitely it's not very easy to solve, but you can define things in this way, and then you can say that then my probability distribution will be e to the minus this energy function, where the partition function is given by summing over x e to the this energy minus energy function. Well, x is the degrees of freedoms that parameterize my sample, and then the theta are some real numbers that parameterize the interaction among these degrees of freedoms. But this kind of model is super difficult to train because there's not only to train, even to sample. To perform Monte Carlo sampling even is very untractable. So therefore, at least we say we need efficient sampling. In order to make the sampling more efficient, Hinton basically proposed the restricted Boltzmann machine, which is a restricted version of Boltzmann machine, which restrict the connectivity between degrees of freedoms. Not only that, he also introduced some latent degrees of freedoms. So there's some visible degree of freedom called x, and the latent degrees of freedom called z, such that the energy function is not just about the visible degrees of freedom, but also the latent degrees of freedom. And there's a coupling theta ij between xi and zj, summing over ij. And such that the probability distribution now is supported on both x and z, which is proportional to e to the minus theta xz. Such that if you want to model the data distribution, that's taking the joint distribution of x and z and marginalize over z. So in this way, because restricted Boltzmann machine puts x variable and z variable on a bipartite graph, so it enables efficient sampling using the so-called Gibbs sampling method, which is essentially first pin the z degree of freedom sample x, pin the x degree of freedom sample, and update z. So this is more efficient than a very general model. But still, it's a bit difficult to compute this log likelihood because it involves summing over this z. But anyway, that was the beginning of generative modeling. So the history takes a long time to actually finally achieve all the three goals. So I'm still at this very early history of a restricted Boltzmann machine. Yeah.
So in physics, usually there are, physical reasons why the energy is, say, analytic, the freedom. Is it obvious that if I'm trying to just introduce some probability distribution, I should then also consider things that go like 1 over x's or things like that, like poles or more complicated analytic structures?
I think that's a basic idea. Like field theory, you just expand in polynomials of field, not in 1 over field.
Maybe you give some examples of x's.
The x is here, like Ising spin. So this is motivated by Ising model. Yeah. Applies to binary images. So this x corresponds to pixel values. For binary image, there's only 2 values, either black or white. So you want to model the joint distribution of that. So you assume that there will be a preference for each site that is parameterized by the first term. There will be correlation between pixels that will be parameterized by the second term. That's why it is reasonable to model in this manner, I think. If you start from a perturbative field theory argument perspective.
These would also be binary?
Yeah.
Z.
Z is also a binary in this case. Yeah.
Connection. Cannot use Z as a gauge to the freedom?
It doesn't satisfy any gauge constraints. Or
it's like there's a physical spin space and there's some for some, for example, spin liquid state. We have some gauge redundancy.
Yeah, there's some. It's a hidden degrees of freedom. You should think of it as a high energy degree of freedom that you integrate out. And X is like a low energy degree of freedom. That's a more appropriate assumption, analogy. Yeah. So, for example, this model only contains two-body interaction, but you can mediate multi-body correlation in X by summing over Z. So that's the point. Okay, but although this model is difficult to train, but Hinton already realized by training such a model, you acquired you basically there's some probability distribution for Z that emerges. So you basically acquire this representation learning ability. And he found that by training this restricted Boltzmann machine, you can use the trend latent feature Z to do image classification. And the effect is amazing, actually, at that time already. So that's a Boltzmann machine. And I want to continue into the Bohr machine, which is a new idea, which is a generative model that runs on the future quantum computer. So you start from some, on the quantum computer, you can prepare some initial state. This represents some pure state, product state. And then you perform unitary evolution by a quantum circuit, and then perform some measurement. And then the measurement outcome will become your x1, x2, all the way to xn. So in mathematical formula, that means at this point, you prepare a state which is parameterized by some theta parameter, where the theta parameter corresponds to the gate parameters in this unitary circuit, which is made of unitary gates, which starts from maybe the all-zero state of n-qubit systems, and then you project it to the so-called X state, which basically corresponds to the tensor product of Xi state, which is the eigenstate of your measurement basis. And then the probability distribution you wish to model, p theta of X, is nothing but the overlap between the state and the basis, and then norm square. So that is how you can also do sampling by keep running the same experiment many times on your quantum device, and then you will obtain these samples. And in terms of sample efficiency, this is very efficient. This sampling even have quantum advantage compared to classical sampling. In fact, quantum advantage in quantum computation was first established in this kind of sampling task. So there's a lot of hope to use a quantum computer to do generative modeling, but the challenge is still it's very difficult to train, because there's no simple way to compute this probability distribution or the log of this distribution. In order to do that, you need to simulate this quantum system on a classical computer, which is also exponentially hard. So that's why people think very hard how to improve these kind of models. So if you think about these models, these two models belongs to equilibrium physics. But if you go beyond equilibrium physics and consider non-equilibrium.
In what sense is the quantum model equilibrium?
I mean, it's ground state of, or it's actually it's not equilibrium. It's also a process of some dynamics, but I mean it's just a state that you always prepare the same state, and it's like you have a. It's like you have a state, and then you always sample from a static distribution, not something that is generated through a dynamical process.
So actual calculation we do is like a variational method.
Yeah, it's like a variational quantum optimization. And then that motivates people to think about dynamics. So modeling, generative modeling using a static probability distribution is too narrow. Generation in its nature should actually be thought as a dynamical process. So it's very natural to think if there is any dynamical process that actually generates data. So there are two famous models. One is called the flow-based model, which is based on fluid dynamics, which try to deform probability distribution through some flow. And then there's another model called the diffusion-based model, which is based on thermodynamics, which is trying to go through a thermalization process and try to inverse the thermalization process in order to generate samples. So that's what I want to talk about in the following. So first of all, let's look at a flow-based model. So the idea of flow-based model is trying to deform the probability distribution from, suppose you have some, let's consider just random number generation. You have some, you want to generate x, x now belongs to a single real number. And then the probability distribution that I desire to generate has a two-peak structure. However, in my computer, I was only able to sample from a Gaussian distribution P of x, which has a single peak. So how can I sample from this two-peak structure distribution from a Gaussian random number generator? The idea is to find a function that maps the sample from here, or numbers from here, to numbers in there. And so this kind of deformation is something we need to learn. So flow-based generative model is trying to create a neural network which learns the process that deforms the distribution from one to another by functionally mapping the variables here to variables there through a bijective map. So where do we get the bijective map? A very natural idea is to go through a flow, which means a time evolution, basically. So I'm drawing this distribution again. So consider this is your x space. This is x, and then this direction is some imaginary time that actually parameterize the deformation between these two distributions. So we can imagine that if you sample a point here, you can try to learn a trajectory that deform the points to, for example, to points there, for example, something like that, and then something like that. So there will be flow lines that connecting points you sample from here to points there, such that it deforms the probability density. So this is t equals 0, and this is t equals 1. We require to learn a model that within time t equals 1 that finish this deformation, such that p of x at t equals 0 is our target distribution, or the data distribution. And then p of x at t equals 1 will be our latent distribution. So the flow will be actually given by an ordinary differential equation, which is dx given by v of x t dt. And then you can also reverse the flow by considering t tilde, which is 1 minus t. And then the reverse flow is very simple. It's also vxt. You just need to reverse the dt direction with a minus sign in your velocity field. So everything boils down to parameterize this velocity field with a theta. Then you can parameterize the flow process and parameterize the deformation of distribution. So the idea is to always start from some trivial distribution. For example, an uncorrelated Gaussian distribution that is easy to sample here, and then learn a super complicated velocity field, no matter what, driven by the data, and then such that this will be your model distribution, p theta of x. Because this v field depends on theta, so definitely the whole thing will depend on theta. Now you can plug this model distribution into whatever your loss function and train it, and the result of the training is actually you know how to flow your data. So that's the idea of a flow-based generative model. So it provides, yeah.
So is that a locality?
You can impose locality into the model. For example, you can, in this V field condition on the current state and predict what is the flow of the next step. So you can condition only in the small region of the current state and predict the flow of the variable in the next time step. Then you can impose locality into the system, into your flow model. Yeah.
But in most problems, people are starting his locality?
Yes. People. Yes, and there are different. There's so many literatures. People have tried different methods. Yeah, locality definitely is a very important consideration. But people also not only consider locality, but also consider hierarchies. Not only locality in real space, but locality in hyperbolic space, in the holographic space. So immediately after proposal of this kind of model, physicists apply it to lattice field theory simulations, where they need to impose not only locality, but also symmetries, but also input ideas of ADS-CFT duality, and those can also be put into this framework. But I want to comment that this model is a model that actually satisfies all the desired features. First of all, it provides efficient sampling because we start from trivial distribution and you just need to solve the ODE, and the solution can be found in order 1 time, so it's very efficient. And then...
Why is it easier to, the space of p theta of x seems to me as complicated, possible p thetas.
Yeah.
But so is the u theta of x and t. Why is that simpler to vary u this flowing the velocity field?
It will be as difficult. These two problems is of the same difficulty, but the only gain we have is that we gain the ability to compute the log likelihood. If you model p theta of x using an energy-based model, you do know how to compute the partition function. But if you model your probability distribution using this, as I want to explain immediately, you can compute log p theta of x following a flow trajectory. So following a trajectory of xt, this will be given by the negative divergence of the velocity field dt. So you just need to start from here and follow the trajectory, and then you can calculate what is the log likelihood. So by solving this coupled differential equation, you can not only draw a sample, but you can also tell what is the log likelihood of each sample you draw from this distribution. So it also provides the third advantage, that you automatically get a latent distribution that is well regularized, also decoupled as a Gaussian distribution. So you can use this, the sample draw from here, the degrees of freedom here as your latent. So that's why this idea immediately caught attention of physicists. And this t doesn't need to be time. It can be the RG time. So this field may correspond to a conformal field theory, and this time corresponding performing RG to conformal field theory. And these degrees of freedom correspond to decoupled massive degree of freedom that live in the holographic bulk. So you can sample. So we know sampling conformal field theory is challenging using Monte Carlo local updates because it suffers from critical slowdown. But if you sample in the holographic bulk, by first learning a holographic mapping, this ODE governs the holographic mapping, then sampling in the bulk, because the bulk field is weakly correlated, so our local update will be efficient. And then the local update in the holographic bulk maps to a global update of all length scales, basically scale-free, on the holographic boundary. So therefore, it provides very efficient sampling that beats the critical slowdown problem for conformal field theory sampling. So that's usage of this kind of models.
So this
Yeah.
so it's motivated by holography and would work very well for lattice QFTs.
Yeah.
But why would it work for images?
Because in image, if you calculate pixel-pixel correlation function, it also satisfies a power law decay behavior. People don't know why, but it's an observation fact. I'm not claiming there's a CFT governing that, but it seems that it makes sense to also map image into the holographic bulk. And indeed, our group,
Images especially? Or?
Yeah, we have done this kind of experiment. and show that using this approach applied to image data sets, you can achieve gains that you can achieve exponential gain in like image correction task. Yeah.
Language.
Yeah, what about language? Language is a bit difficult because language tokens are discrete. You can see this flow-based generative model use continuous differential equation. At least for the model that I described here. There are also discrete flow-based model, which I'm not touching here. But currently, it's not very much used in language.
So for the quickness slowing down for CFT,
Yeah.
how does that rely on the assumption that there is a holographic view of the CFT?
Yeah, so maybe there's not a human non-holographic dual, but the model is trying to learn some approximation of the holographic dual. And then for sampling problem, you don't need the exact holographic dual because you don't rely completely on this model to do sampling, because there's still an underlying Monte Carlo sampling that's going. So you just use the learned model to propose new samples. Whether to accept or reject the sample, you still rely on energy evaluation. So you're not deviating from the detail balance. So you're just learning a model in order to improve your acceptance rate, basically. Yeah.
I'm still profoundly puzzled. It's very clear what's happening in this nice one-dimensional picture with Zhuang. But in some infinitely dimensional space, these things become functional.
Yeah.
And the bottom line is the probability distribution on the left is some entangled thing full of correlations perhaps described by some very high-order polynomial which is related to the sample.
Yeah.
Yet the assumption is that there is some diffeomorphism that turns it into uncorrelated sampling.
Yeah. So this X is a field.
So is there a theorem that says that
there's no theorem, so machine learning is all heuristic, no theorem, it's all trying.
But isn't it saying that, well, we can learn simple things that are factorizable and runnable?
Yeah, it's
that are actually more complex. We still quite tackle it.
That's a beautiful hope, right? Yeah. That's okay.
Just following up on the second to last question. So, for instance, let's think about just the Ising model, the lattice, near criticality. So there's also a slowdown near criticality.
Yeah.
So how? And this example doesn't, as far as we know, doesn't have a nice weakly coupled.
Yeah, that's true. That's true.
So, do you have any intuition? Well, first of all, does it work to do this procedure? Does it beat Monte Carlo, for example? And second, do you know why it works? If so.
There's improvement.
Okay.
People see improvements, not in Ising model, but in lambda 5-4 theories, which is close to real lambda 5-4 theory, close to Ising model, right? So it does beat Monte Carlo, but the training cost is a lot. And then during the inference, you need to solve, during sampling inference, you need to solve differential equation. That's also a pain in the ass. So it's also, so eventually the running time still doesn't beat Monte Carlo if you take all this into account. But it's an interesting idea still,
So suppose I want to start the 5-4 theory, right?
Yeah.
So, let's forget about whether it's efficient or not. Just conceptually,
Yeah.
I mean, we don't really know the holographic theory, do you, in the bulk, right? So how does it work again? Can you explain that? So,
We know or we don't know.
I mean, we don't know the holographic
we don't know.
5-4 theory.
Yeah.
So, but you mentioned that this can still use the holographic theory in some way. Can you explain again how this works?
It just forced the model to learn a flow in the hyperbolic space. No matter what kind of flow it learns, it's not our responsibility. The model will learn it from the data.
You interpret that as a holographic.
You interpret that as, You are not saying that I input a holographic model. I'm not doing that. Okay, so.
Point you jumped from images and pixels to holographic theories. So I was trying to understand. So when you said that there is some power law correlation. So that's on real images of cats and dogs.
Yeah.
I
I guess the question I have is, when I'm looking at the flow-based model, it's just Fokker-Planck's equation that gives you this, right?
Yeah.
And looking at RBM, and there is a half a century distance between those two coming up. Like, what was the reason? What did we have so that we could do the flow-based models that we didn't have at the time of, let's say, RBMs? Like, why did it take the field, let's say, half a century to just like
half a century?
Like, I thought RBMs were in 1970, if I remember correctly. It's like 10 years ago, right?
I don't know why. I'm not a computer scientist, so yeah, I started researching these fields 8 years ago. So
okay, so let me ask you like this, right? Is there any new numerical or something like that capability that sort of made these desirable, or was it just that we didn't realize their potential until 10 years ago?
Yeah. So that's what I said. There's some desired feature there, and it takes time for people to design model like that to realize all these features. Finally, a lesson that we learn is that physicists has already invented a lot of beautiful theories, and then we need to learn from physics and design generative models, not just sit there and think about how to model probability distribution. Yeah.
Can you give some insight why we should think of using a Gaussian in the latent state?
No, there's no requirement that it needs to be Gaussian. It just needs this distribution to be efficiently sampleable. And Gaussian is one example. You can also uniform distribution, no problem. Yeah.
You can use that for CFTs, even though they're very spread out.
Maybe, yeah. It relies on the flow to realize this spread out. Okay, so if you have already this flow-based idea, why not? There's another a very important dynamical process is called diffusion. And then diffusion-based model is very similar to flow-based model. Again, you want to deform distribution to distributions, but not through a deterministic process, but through a stochastic process, where you still go from t equals 0 to t equals 1, but this time you go through this, I just randomly draw some passes that there's a stochastic differential equation that governs the dynamics. So the forward dynamics that goes from the target distribution to latent is given by some f of xt dt and then plus g times dw. Well, this dw is some Werner process whose expectation value is 0, and then the second moment is of order dt, and it's uncorrelated. So that is the forward process. And then the motivation that people consider diffusion-based model was because exactly in dealing with flow-based models and solving this differential equation, it's very time-consuming. So everything, and therefore the model is quite difficult to train still. And then people thought about how to improve it, because in training this model, you're basically computing this probability distribution and compare that with your data distribution. So there's only one point. You are comparing your model with your data. So that means all the loss function, all the gradient signal need to propagate through the whole differential equation to train all the parameters inside. And that's why it's a very weak training signal. So the idea is maybe we should consider some different loss function. So the conventional loss function of a KL divergence between data and the model distribution basically corresponds to you sample from the data and then you compare the log likelihood of data and the log likelihood of your model. But there's another divergence measure that people actually also used in statistics, which is called the Fisher information, which corresponds to the expectation value of still drawing samples from the data, and then you compare not the log likelihood, but the gradient of the log likelihood of data, and then minus the gradient of the log likelihood of your model, norm squared. So instead of bringing the data distribution close to the model distribution close to data, you can also bring in the gradient of the model distribution close to data. So if if there's a probability distribution that looks like a Gaussian, then the physical meaning of the negative log likelihood is actually like a potential function such that the Gaussian distribution is the static thermodynamical equilibrium distribution of this energy function. And the gradient of this log likelihood, or negative gradient, exactly corresponds to the force that a particle will experience in this potential. So instead of comparing the distribution point by point, you can also compare the force field point by point and require the corresponding force field to match at every point. But this is very so you will encounter an object like this. You need to know what is the gradient of data distribution. And in fact, this object has a name. You can model it by a neural network on the model side. And this is called the score function. And then in physics, it's actually the force field. But I don't know, in computer science, it's just called the score function. And then you want to match the model score function with the data score function. But the data score function, where do I get that gradient, right? So then people come up with very clever idea. It turns out that in the stochastic diffusion process, if you run the forward diffusion in this manner, the backward diffusion will be governed by another SDE, which the score function exactly appears as g squared as xt dt, and then plus g dw. The reason is that you can see that the force field is trying to apply a negative pressure that counters the diffusion pressure. Because if you have a distribution, have a single peak like this, under diffusion or under random walk, the peak will spread out. And then that's like the thermal pressure that push the distribution apart. And then the score function is exactly the force field that tries to maintain this peak and bind it together. So that's why if you want to reverse the diffusion, what you need to do is to apply the score function as a negative pressure to your distribution, such that under diffusion you can push your probability back. So that's why the score function will appear in the reverse diffusion. And then this time will be the reverse time. So if you run a forward time, the reverse time is 1 minus t, which means you can sample from your data set and run a forward diffusion process and collect the data, collect the samples at different time. And then you can use the samples and plug in this reverse diffusion equation to train your score function. Now you have samples to train the score function by comparing the mismatch between the drift terms in the forward process and the backward process. So that is the beauty that the diffusion process provides us. It provides us a way to match the score from the data directly, such that we can learn how to generate data from a trivial distribution. So the idea, or philosophical idea, of diffusion model, you can see you start from some structured distribution, and under diffusion you remove all the structure in your diffusion under thermalization. And then you are learning actually how to construct from destructions. So that's philosophically, I think, it's a very deep idea. And then during this process, in the forward process, entropy is increasing, and then you are actually reversing the error of time to decrease the entropy. As a physicist, you may ask, how can that happen? It is because if you leave the system unmonitored, then of course entropy increasing process is irreversible. But if you monitor the system and take data from the forward diffusion process, use the data to train a neural network, to train artificial intelligence. Intelligence is learning information from your data, and then it is using the information and injecting the information into the system in the backward process to reduce the entropy. So that's how yes, it's a Maxwell demon to counter the entropy increase and then to reverse the error of time. So that's, I think the most valuable usage of artificial intelligence is to reverse the error of time. And then you can see I'm leaving a missing piece here. So there must be something here which corresponds to a generative model which is both quantum and dynamical. So that is actually the recent progress in our field, which is quantum diffusion model, which is a diffusion model which runs on a quantum computer. And the idea is that nowadays quantum device, what you can do is you can perform weak measurements of a observable O on a state, on a quantum state, psi, and under this measurement, your state will undergo a quantum state collapse. And the state collapse is exactly a stochastic process described by the following stochastic differential equation acting on psi. Well, this delta O corresponds to your Hermitian operator, which corresponds to the observable. And then, yeah. So that's the SDE. If you look, it's very similar. You just need to match every term. There's a drift term and there's a noise term. So you can borrow all the score matching technology that you learn from classical diffusion to train a reverse diffusion model that takes data from your quantum device through weak measurement and learn how to reverse the quantum diffusion process. So if you can succeed in such a training, what you gain is an AI model that learns quantum state preparation. So if you train your model on states, let's say random states in the code subspace of a quantum error correction code, then essentially you basically have a quantum error correction decoder that is data driven, and automatically that will bring you back to the code subspace from any quantum state. So this is also, by training this kind of model, you can achieve so-called algorithmic cooling. So this is using information processing, classical information processing, to cool the system. So in the future, I'm imagining that when we want to build a quantum computer, the quantum chip is not only embedded in a dilution refrigerator, it is actually first embedded in a generative diffusion model. And the diffusion model is using algorithms to first cool the system, and everything now is embedded in a dilution refrigerator to further physically cool the whole system. Yeah.
Quickly, but weak measurements give you very little information. So I was always skeptical of this idea of quantum diffusion models because diffusion models do something that very fundamentally goes against what quantum physics can give us in terms of information. So my question is like, do weak measurements really give you information that is even of the order of what you need here to reverse the process? Yeah.
So the trajectory of the weak measurement gives you sufficient information. You need to collect the whole time trajectory of weak measurement. At the beginning, the model cannot infer anything about the state. And you are pointing out a very fundamental problem here. So the fundamental difference between quantum and classical diffusion model is classical model, you directly can observe the state of your system, which is X. But in quantum system, states and observable are separate. So you don't know what's the state. You can only infer the state from measurement outcomes.
Okay, weak information and indirect information.
Yeah. So it's more challenging.
And at scale, that's supposed to work. I'm very curious.
Yeah. It turns out that it can work. So there are already of all the 10 papers in this direction. So this is some new progress. But
is it deterministic preparation?
It's a stochastic preparation.
You mean for every trajectory does it converge to the correct state?
Every trajectory doesn't converge to the correct state, but can converge to the probability distribution. We are converging we're learning to converge this distribution, not to converge to any single state. Yeah. Okay, so finally, I just want to make a few comments that since we have seen that there's a close relation between generative models and all different kinds of physics theories. So we may wonder, maybe the way that we formulate physics theories also need to be upgraded. So conventionally, as theoretical physicists, when we talk about what's your theory about the physical system, you say, oh, let's consider the following Hamiltonian. Let's consider the following action. But now we know that Hamiltonian action formulation is just correspond to a tiny corner of generative model. So in the future, when we talk about physics theory of a physical system, we shall ask, what's your generative model? And then what's the parameters in your generative models are the parameter of your physics theories. So immediately there is two related questions to condensed matter theorists. How to classify phases of generative models. Secondly, how to perform renormalization group of generative models. So there are also studies along those directions. For example, renormalization groups relies on the ability that generative models can perform representation learning such that it automatically learns to extract so-called relevant features because it compresses. So suppose X is your few degrees of freedom, and then this Z will be the latent degrees of freedom that's supposed to correspond to some relevant features in your field. So this generative model, if you plug into that kind of perspective, you can use your field samples to train a generative model that maybe learns conditional distribution that correspond to the RG transformation, and then it learns a prior distribution of the latent that correspond to a new model, and then this process will induce a parameter flow. This parameter flow will correspond to the RG flow of your generative model. And then if you try to match this parameter flow using another flow-based model, saying that there's a gradient of a monotone, RG monotone function, which can capture this parameter flow, then you can basically figure out how generative model flows in the parameter space of all generative models. And through that, you can probably discover new CFT fixed points and so on. Yeah.
Thank you.
Yeah.
More questions. Anybody but Sankey or David first? Yes.
Can I ask more about this big measurement?
Yes.
So the equation that you described, that's the equation of I have a quantum dot and I'm measuring it with a quantum point form. Or I have superconducting qubits in a cavity and I'm measuring what speed came out of the cavity, right? So what would I physically then do to train this kind of model? Like, is it, can I already see me sitting and measuring as a training?
Yeah. Training still is a problem. It's still variational training.
And what am I minimizing then?
You are minimizing. You are training a score function, and it turns out that the score function will correspond to a Hamiltonian. That actually you need to plug into because score function corresponds to a drift term. And drift term in the quantum sense is a Hamiltonian that drives the unitary evolution, unitary feedback that is conditioned on the measurement outcome. So you are learning a unitary feedback that conditioned on the measurement outcome. And then the unitary feedback is implemented by a bunch of gate parameters that is predicted by a neural network which takes your measurement outcome and processes it and predict the gate parameters. And then you need to train basically every parameter in your neural network. And there's no gradient descent because gradient chain is missing. But so training is a problem, I admit. But maybe in the future there will be, there is indeed gradient-free optimization approaches that can be used in this context.
So you've given a bunch of examples.
Yeah.
According to what you say, almost all of the recent advances are based in physics,
Yeah.
which is good for physicists. But in your last remarks, you seem to hint, maybe I was wrong, that physics can learn something from these machines aside from doing calculations, something deep.
Oh.
Is that what you're thinking?
Yeah, I'm thinking maybe we can reformulate future physics theory in terms of generative model.
But that's not what you talked about. You've talked about quite the opposite.
Yeah, I've talked about how to use physics to motivate. Historically, physics has motivated the development of generative modeling. Yeah.
And these are all examples.
Yeah.
And these are new examples.
Yeah.
But how? Give me. So you're dreaming of going in the opposite direction.
Yeah.
Can you elaborate on that?
Yeah. So, for example, you can you can do this machine learning RG that basically parameterize your field theory as a machine learning model and try to learn the RG flow of generative model parameter instead of Hamiltonian parameters or action parameters. Yeah.
But do you think this would yield some?
Yeah, this yields. This doesn't yield for now. Currently, doesn't yield any new physics. It just rediscover Ising critical points and things like that. But it does give you prediction powers. Yeah. It gives you. You can use it to compute critical exponent of those critical points. Yeah.
Right. So I wonder how much can how much can generative model actually describe a quantum system, for example? So here what you learn is the probability, but we know quantum system more than probability. There's also phase in superposition, right? So can actually learn that,
Yeah, that's another question I didn't talk about. It's a learnability issue. So it's not conceivable. We should not believe that a classical generative model can learn anything about quantum system. Otherwise, there's no point to build a quantum computer. So definitely, the answer is no. But another thing, what you ask about, like the phase. So indeed, from what we learn about classical shadow tomography, anything in the quantum state is already captured by the measurement outcome, probability joint distribution of measurement outcome. In a tomographically complete basis. As long as you have a tomographically complete basis and you know the joint distribution of measurement outcome in there, there's nothing more you need to learn about quantum systems.
So you need to train your model with
yes.
all those data.
Yes, you shouldn't train your model. You should never train your model in a fixed basis. You should always think about training your model in tomographically complete basis. That's the lesson we learned.